Okay, we're going to talk about some guidelines that are in this. Are there any of those left over, by the way?
One.
One? Can I have it? Thanks. So these are guidelines. They're not hard and fast rules. It's a real mess because the data can be analyzed in multiple ways. There's not one right answer when it comes to stats, which can seem a little non-systematic, right? It might seem like, that doesn't sound quite right. But it just means that if you do have that situation where you didn't think about the analysis ahead of time, there are some ways in which you can analyze the data that are perhaps not ideal, but are still going to get you the answer to your question. So, yeah, so these are guidelines. Okay, so you have your independent variable and your dependent variable. These are the two most important terms. You need to know which one's your IV and which one's your DV. And you need to make sure that and often we're thinking about the dependent variable when we're choosing a test. So for example, with regression, you cannot do a regular multiple regression, unless you have a continuous outcome variable. So you want your dependent variable to be continuous. If your dependent variable happens to be dichotomous, yes, no, then you can use a logistic regression, but it changes your analysis entirely. So your independent and dependent variables are most important for you to understand. If a variable is categorical, that means that it's classifying something. So gender is a categorical variable. Well, it's being looked at as more of a continuous variable in a lot of research now, but in terms of gender, we can use it as a categorical variable. Then there's a control variable. Control variable is like something, as you mentioned when you were talking about causality, the variables that you're controlling for in order to assess that outcome variable, the link between your predictor to your outcome variables. So you might want to control, we often control for relationship length, because when couples have been together for a long time, their sex life changes, right? When we also Control for things like age, because we know that sexual functioning differs as you get older. Those are good examples of control variables. And extraneous variables are things that we don't control. We didn't measure it, maybe we thought about it later, oops. But it's just something that you put into the limitations, you take that into account as you're analyzing the data and you understand that this probably is having an impact here. We didn't control for it, we can't control for it. That's just how that goes. And then a confounding variable is just a more problematic extraneous variable. So it's where there's a systematic relationship here, where we can see if we were to group different participants together, we'd be able to see patterns of the ways in which this variable is impacted. And then a dummy variable is something that you might construct for the use in certain analyses. So we use dummy variables a lot with gender, unfortunately. We shouldn't, but we use dummy variables. You code them as 0 and 1. Another dummy variable we code, so if we're looking at infidelity, we'll code whether they engaged in infidelity or not as 0 and 1, and those are used then as our outcome variable in our logistic regression. Do I have you guys still? You're following? Okay. And then nominal data there's no sort of link between the classifications, right? Gender, occupation, things that aren't like ranked. Whereas ordinal is things that do have, they do have sort of distinct space between them. So you might ask something like, how satisfied are you? I strongly agree, or I'm very satisfied in my relationship, strongly agree, neutral, disagree, strongly disagree. So these are called Likert type scales. And those ordinal variables are often treated as continuous, by the way. And then intervals is when there is an important and notable difference between know that there is a standardized difference between 30 degrees Celsius and 20 degrees Celsius. Sorry, Fahrenheit. So, yeah, a ratio is something like your height or your weight. So also there is a difference between these. Honestly, pretty much like if you've got interval or ordinal or ratio, those are all going to be treated as continuous variables in an analysis, okay? Nominal is where it'll be treated as a categorical variable. And really, like when it comes to actually doing stats, those are the most important things, that you know the difference between a categorical variable and a continuous variable. Yes, categorical or nominal, and continuous can be or ratio. Yeah. Okay, so those are your terms. In the stats world, there's these two main areas of stats. There's parametric tests and there's non-parametric tests. The parametric ones are built on the assumption that you have some amount of normality in your population of interest, or that your sample was drawn from a population that you can assume is normal. So if you're using a convenience sample, we probably aren't drawing a normal distribution. Yet, if you look at all these papers that people publish all the time, very rarely are people paying attention to this, but it is important. And I'm going to talk about why it's important. So these are parametric tests, and there are ways in which you can see if your data are normally distributed, but there are not necessarily always ways for you to know if your sample is is a normal representation of the population of interest. And then when you don't have assumptions about that population that you drew from, those are non-parametric tests. And neither are harder than the other. Like, I feel like people just go to parametric tests because if they think it's easier or something. They might be more familiar names, but they're no different in terms of like being able to, being able to actually read the output. It just means you click a few different buttons. It's not that big of a deal now. Now, when we used to do it by hand, sure, I can see like why people got this in their head, but not now. So there's a whole world of Ryan Gosling memes that have like statistics, funny statistics things. It's amazing. So data are non-normal based on skewness. And if you know what skewness is, that means that you look at, so skewness and kurtosis is usually best assessed by looking at a graph. If you just look at a visual representation of your data, that's the easiest way to tell if your data are skewed or not. Remembering that a normal distribution is something that looks like, well, it's like a bell curve, right? Whereas if it's skewed or if there's a problem with kurtosis, then you're going to see like this, or you're going to see like this. It'll look weird. It won't look like a bell. So you can look at a graph, just a normal plot, or even you can just look at a histogram and see how well it fits. Or you can test normality with a test that SPSS offers. Is SPSS something that's familiar to all of you? Sort of? You know what it is at least? Yeah, so when I say SPSS, you know what I'm talking about? Okay. So you can just click a button and it gives you this. And again, this is where like stats has come a long way and is pretty accessible. So sometimes it can be hard to tell if you should use the non-parametric version of a test. But what they do is they rank the outcome variable from low to high, and then instead of analyzing it as if it's this continuous variable, they analyze it based on that ranking. So that's what it's doing mathematically behind the scenes. It's not really important for any of you to know, unless you want to go into stats. So, as I mentioned, you choose that parametric test if you're sure that there's an approximate normal distribution from where you selected your sample. But you choose a non-parametric test if the outcome is clearly not normal. So say you're drawing from a really wealthy area or a really poor area. Or if some participants, some values are off the scale. So some participants end up like choosing strongly agree on like a number of variables, and it just indicates to you, well, they may not have been paying attention. You can test for that and delete those cases. Or they might have been, it might just be that there are a lot of participants where your scale is not measuring it quite right for them, in which case you're going to want to do non-parametric. Or when it's clearly not normal when you look at that bell curve. You can transform the distributions to become normal so that you can use parametric tests if you want. You do that by like using a Z-score, where you just like standardize based on the Z-score, and that can be done as well in the context of a Z-score. I see all of you being like, what is this Z-score? Yes, so you can transform this to become transform using those Z-scores, and that will make the distribution normal. But you really don't need to bother doing that because you can just do a non-parametric test. It's up to you. Okay, there are a few ways to tell them. So, if your sample size is large, then you can examine distribution using you can use this test, Kolmogorov-Smirnov test, to statistically test whether it's normal or not. If your sample is less than 100 though, and many of you who are doing like lab-based stuff, your sample is always going to be less than 100, probably, most of the time. Our samples are very rarely under 100. We wouldn't be able to answer our research questions without more than that. So our sample sizes are usually, we run into the opposite problem of like the last survey thing that we did, I think we had like 14,000 people. So if your sample is small, then it's going to be difficult to detect using those visuals. So you really need to consider the non-parametric based on just where you took your population. And also looking at previous data, looking at what other people had done. Did they use parametric tests or did they use non-parametric? Because if you end up using parametric tests, and then a reviewer comes back and they say to you, a reviewer being like when you submit the paper for peer review, and they come back and say, you should have used a non-parametric test, you can say to them, well, actually, this study used a parametric test, and we drew our sample from a very similar sample that they did. You can use that as your rationale. I don't think it's great practice. I think that instead you'd be better off just doing these non-parametric tests to be accurate, but it is a way that you can argue that. So making sure that you're doing that step if you're going to use parametric. So Cameron, you ran into this problem actually with our data with outliers of number of partners, right? So if you have a lot of outliers, like there were some that had hundreds, thousands of sexual partners that they listed. So they were probably, what, how many? 24,000, not 2,400. Okay, still. So that's a busy person, definitely an outlier in our data. We need to make sure that we look at that source of that scatter. So that scatter is probably either a data entry error, like an error of theirs when they entered their response, or they might be engaging in sex work, or they might be somebody who is counting their partners from sex work when we ask them not to do that, when we ask them to do it just from non-paid sex. But so this is, that's one example where you would just like remove that outlier and then take a look at the scatter plot without that for those people. So really, how much does it matter? It matters a lot if you have a small n. It matters not a whole lot if you have a large n. And that's why I stress this point, especially in this class, is because many of you are going to be working with small data sets. And so it matters more when you have those smaller data sets, whether or not you use a parametric or non-parametric test. When you have large samples, there's just enough, it's robust enough that you're getting rid of some of that noise just by the sample itself. Okay, so p-values. Any questions about parametric or non-parametric? Kind of really exhausted that point. Okay. So typically we use a p-value of less than 0.05, right? But they can range. And I'll talk later on, after I get through all of the different types of tests, or all of them that we're going to cover today. I will talk about adjustments that need to be made to the p-value sometimes if you're doing multiple comparisons. That's called a Bonferroni adjustment. We'll talk about that later. But pretty standard is that you use p is less than 0.05, because then you can be 95% confident of whatever you're confident of. Like Ryan Gosling is confident that I'm the one for him. And you can use, some people use p is less than 0.01 to be more conservative about it, or as high as p is less than 0.10 to be less conservative. Pretty rare to see that though. Usually it goes in the other direction because it's better to be more conservative than less when it comes to statistics. Okay, one-tailed or two-tailed. If you're in doubt, just use a two-tailed. That's an easy guideline. But one-tailed is appropriate when you are certain that, and you were certain of this before you collected any data. This is not like, oh, I did a quick little correlation to see what this might be. No. If you are certain before collecting any data that there will either be no difference or that the difference will go in a specific direction, then, and if you're positive that there's going to be no difference, then you probably are asking a student research question. Because why would you bother testing that, right? But if you're certain before you collect the data that it's going to go in one direction, then you can use a one-tailed. Otherwise, you're going to use a two-tailed test. And two-tailed is the default when it comes to, two-tailed is the default in SPSS. Errors. So that type 1 error, remember,